There it is. Okay. I think this is recording. It's going to look weird when you go watch that mall looking at me. All right, so today, what we're going to do, this class has been chosen to do that survey. You don't know what I'm talking about? I have no control over this. We were supposed to finish it by the 30th of September. So I'm a little late on it, but we're going to do that at the end of class. All right? And that's just, that's how they gather information for college purposes. But we are going to do 8.6 today out of the book. We're starting a new section. 8.6 is titled Radical Functions and Radical Equations. Right? We are only going to do the equations part of it. We're not going to do the functions. So I'm just going to call this radical equations. Now, just so we're all clear, we've done something like this already. We did square root equations, and that appeared on your test. Those are the ones where you had square roots, and we had a process. Remember the process? Isolate the square root, square both sides. We are going to be doing the exact same thing, with the exception that we are not going to be confined to square roots. We may have cube roots, or fourth roots, or fifth roots, or sixth roots. So instead of saying square root equations, we say radical equations to represent a more general type of equation. But the process is the same. Okay? So let's start out with an example. And if anyone have the book that I could just borrow real quick? Well, let me make sure I don't have it. I grabbed everything but that. Be careful. You just leave it on your desk. I'll just look off. Yeah. All right. Yeah, something simple like that. All right, how about something like this?
Do you need my name on each individual sheet?
Well,
I can do it. It's fine. There's
I'm okay.
4.
I'm okay.
You sure?
Yeah,
Okay.
this is good. I can see your handwriting. It's easy to follow. Okay, there's the equation. So that looks very much like the square root equations, right?
What?
I'm videotaping, so if you walk through there, it's going to... I'm just letting you know. I don't want you to be videotaped without your permission. Okay. But you can go around. Yes, put them there. All right, so equation, right? We have a root, but it's no longer square root, right? I have the 3 there, that means cube root. So what were the steps in the process that we had in the past? Isolate it. Isolate the root, right? Here, we have the root isolated, don't we? So steps are exactly the same. First thing, isolate, right? Check, we got it, right? Step 2 was what? Square. It was square both sides, right? But see, we won't be able to do square both sides because it's a cube root. So squaring won't eliminate the cube root like it does the square root. So what do you think we do to both sides instead of squaring? We cube it, right? If you're taking a cube root and you want to undo the cube root, you cube both sides. So you raise both sides to the 3rd power. So I'm going to raise both sides to, in this case, the 3rd power. And the 3 is coming from the fact that we have a 3 up there, right? So let's go ahead and do that. I'll raise both sides to the 3rd power. This is going to be hard to do, but I'm trying to stay within this one frame. So here we go. I'm going to take the cube root on the left, 3x minus 4. I'm going to cube it. And then on the right side, I take the 4 and I cube it. If y'all need to move this, definitely you. If you need to, I think y'all need to like move this whole table over so you're not trying to see that board like that. Or you move around or something. Okay, so cubing this side, what'll happen? Cubing a cube root, this goes away, okay? But you're left with what's underneath. That's still called the radicand, but we'll just say it's whatever's underneath. So 3x minus 4 will be left on the left side. On the right side, 12? 64, good. Okay, 4 times 4 times 4, not 4 times 3. So I'll continue up here. What we have now is 3x minus 4 equals 4 times 4 times 4 is 64. And this equation should be pretty okay to look at, I guess. It's a linear equation, right? So isolate x, get x by itself. So add 4 to both sides. So you'll have, what, 3x equals 68, and divide both sides by 3. 68 divided by 3, that's not an integer, right? It's a decimal something, so you could find it as a decimal, but we just leave it as a fraction. Okay? That's it. So our answer is 68 thirds. Now, oh, I forgot. What was the, we isolated, we raised both sides. Repeat if necessary, right? But we always skip that. Please put that here. Skip that step. And then the fourth step was the solving, right? Got ahead of myself. Because we have a fifth step that we haven't done, which is to what? Check. Okay, so let's check it. So let's go back over here to the original. Oh my God. There's got to be better grocery. Let's see if that one's. Okay, thanks. Yeah, much better. Okay, so we're going to check. So when we check, we take the answer, we plug it into the original problem, right? So I'm going to take the original problem here. Cube root 3 times x is 68 over 3 minus 4 equals 4, right? What's that 3 times 68 thirds turn into? What's this? What happens here? What cancels? The 3's, right? This is really like a 3 over 1. So the 3's on top, this 3's on the bottom, so these 3's cancel. And you're left. Oh. I'm not. I'm okay, I feel fine. Okay, what is this? Cube root of 68, but then take away 4. So what? 64? Question is, does that equal 4? Yes. Yes, right? Cube root of 64 is what number times itself? 3 times gives you 64. 4. So that checks, doesn't it? We're good. That worked. We happy? Okay. No questions? So let's go on to a different problem. How about this? Change it just a little bit. How about we have, I'll give myself some more room. How about we have this example? Fifth root of 5 minus 2x plus 2 equals 0. So this is a radical equation, right? Yes. Okay, so let's go through the steps. Isolate the root. Right now is the root isolated?
No.
No.
Subtract 2 of those.
So bring the 2 over. So I'm going to isolate first by bringing the 2 to the other side. That means I subtract it on both sides. So my new equation, isolated, would be the fifth root 5 minus 2x equals -2. Okay, it's isolated. Now what?
You raise both sides to the fifth power.
Fifth power. Raise to fifth power. And that's always dictated by whatever number was out there, right? So on the left side, when I take the fifth root, 5 minus 2x, and I raise it to the fifth, I get something. And on the other side, I take -2 and raise it to the fifth.
It's gonna be a.
Okay, so this one right here cancels out, right? And you just get the 5 minus 2x. On the right side, what was it? I heard it. -32. Just be careful with the signs there. Negative times negative times negative times negative times negative. So 5 negatives multiplied would end with a negative also. Okay, step 3. Do you see any more radicals anywhere? No, we're going to skip. And again, this isn't going to happen to you in this class. We're going to be nice. Okay, step 4, solve this equation. Five minus 2x equals -32. So try and get x by itself. So subtract 5, that's one way to go. That's the way I would do it here. We have the -2x is still here on the left. On the right, -37 now. Then divide by -2. So when you divide a negative by a negative, you get a positive. So 37 over 2, again, is a fraction that does not reduce. And so you just leave it like that. Because I divided -37 by -2. Negative on both sides. So I got a positive answer. Last step is to check. So I'll do that right under here. Hey, how's it going? So checking is fifth root 5 minus 2 times, now my x is going to be 37 over 2. And then plus 2 equals 0. So that's what I'm trying to figure out if that's true or not. Those 2's cancel, just like the 3's did in the previous problem. I have the fifth root of 5 minus 37. That's okay. 5 minus 37 is -32, right? -32. And can we take the fifth root of a negative number?
No.
Yes.
We can't do square root, right? And we talked about in class, you can never take an even root of a negative number, but an odd root you can. So we're trying to figure out what number times itself 5 times gives us 32, but it has to be a negative answer. So -2. So this right here is -2 from work that we've done, prior to this. We've looked at that before. That should be -2, and then this is plus 2. And does that equal 0? Yes, so it checks. I'm excited. I'm going to do something I've never done this weekend.
What?
I'm going hunting.
You're on a bird hunt.
I don't even know. I honestly don't know.
What kind of gun to take?
It's not going to be my gun.
Oh.
It's my neighbor. He's a big hunter.
Oh.
But I'm not excited because if I have to shoot an animal, I'm probably going to miss it on purpose anyway. But I'm excited because he's asked me to help him. He has this night vision scope that has a video output on it, So I've put together a wireless adapter that'll go onto it, and then everyone who's with him hunting can sit there with a little camera screen and watch him hunt and record it at the same time. Yeah, so I'm excited to see if the technology that I put together works. But you know, as far as the shooting animals, okay, we'll see. All right,
You might like it.
I might like it. I might. Who knows? Does this all make sense though? I mean, like, it's pretty much the same thing. We have to be a little careful with, you know, like maybe some of those fifth roots or something like that, like when we were checking. But just like in our other problems, you know, they get a little complicated because you can have more than one root. So let's take a look at something like this. What about fourth root 2x plus 1 minus fourth root 5x plus 7 equals 0. Well, what do you think? We have to isolate one of the roots, right? So we get to choose either one.
Didn't you say that it's better to get rid of the negative one first?
Yes. I mean, I would leave this one here and move this one to the other side. So in the isolation step, what I'm basically going to do, I brought some different colors today. Let's see. This isn't the one I brought, but oh, that looks okay. I'm going to add this root to both sides, the whole root, right? So this is the 5x plus 7 on this side, root, well, fourth root. 5x plus 7 over here also. All right, so my new equation will be fourth root 2x plus 1, what?
And plus
Equals just that fourth root 5x plus 7. There we go. So I have isolated one of the roots, one of the radicals. And then I do what? Fourth power both sides. So second step, raise to the fourth power. And although it may look ugly, it's actually going to be really nice, because what happens when we raise something to a power on both sides? When we raise the fourth to fourth root here, it'll go on both sides. So let me write that out though. We're going to have fourth root 2x plus 1. I'm going to raise that to the fourth. And then fourth root 5x plus 7. Raise that to the fourth power. Both the radicals cancel on both sides. And we get 2x plus 1 equals 5x plus 7. This is a linear equation. So we're going to solve it after we skip the third step. Yeah, get all your x's on one side, all your numbers on the other. Which side you go to doesn't matter. But I like your idea. Move the 2x on this side, subtract 2x, and then you need to move the 7 on the other side. So here's my solving step. Solve, this is the fourth step. So I'm going to take my 2x plus 1, 5x plus 7, subtract 2x here, which means you subtract 2x here. Subtract 7 here, subtract 7 here. So the 2 x's are gone, the 7's gone over here. Negative 6 equals what?
3x.
3x. right? 1 take away 7 is negative 6. 5x minus 2x is 3x. Divide, x is what? X is negative 2. So our potential answer here is x is negative 2. But now we check it. So we have to plug it in there. Okay, here we go. 4th root of 2 times negative 2 plus 1 minus 4th root of 5 times negative 2 plus 7. Are those the same? That's the question. So what's 2 times negative 2? Negative 4 plus 1? Careful. Negative 3. Right? And then over here, what do we get? 4th root of negative, this is negative 10, plus 7 is negative 3.
Yes.
Does that equal 0? Well, this is a tricky question here.
I got lost on, because you subtracted 2x on both sides, which would leave 1 equals 3x plus 7.
Okay, and then take
Did you
7 away.
subtract 1? Oh, I didn't.
Take 7 away from both sides.
Oh.
So what do we think about this? Yes or no?
No.
This right here is exactly the same as this right here, right? And I'm subtracting it. So if I take something and I take away that exact thing, shouldn't I get 0? So it appears to be true, doesn't it? The issue we have, though, is the fact that we're trying to say that the 4th root of negative 3 is something that makes sense. Right? Remember we said we can never take an even root of a negative number. Even root negative number. So this right here, to us, we always said this is a non-real number. Well, today, we're actually going to start talking about taking roots of negatives. We're going to start talking about the imaginary numbers today. So this is going to be okay. All right, this is going to check out. Because it's something minus the same exact thing, that equals 0. All right, do you think you understand the method behind this? That's pretty much it for this section. I'm not going to go beyond this. You may recall, like on your test, we had problems where when you squared both sides, and a lot of you missed this problem. The one where you had to move the x to the other side, and then when you squared it, you had to FOIL. I don't know which one I'm talking about. That problem, you're not going to have anything like this here. And the reason why is because squaring both sides was easy in the sense that you could FOIL out. But imagine if it was fifth power on both sides. You had something like x plus 2 to the 5th power. You'd have to do, I don't know if you'll understand what I'm saying. Maybe if I just show you like what I'm trying to explain. If you had a problem like this versus something like this, this is something that I could have asked you on the last test. Because you isolate the root, it is isolated. You square both sides, so when you square the left, it's x plus 1, right? You square the right, you have to do x plus 2 times x plus 2, which means you FOIL, correct? And then it's a quadratic equation, you have to work through it. Here, if I did the same thing, you'd have to do what power on both sides? 5 and 5. This would go away, but what about this?
That's 5.
That's 5 of these. What's that? See what I'm saying? And this would be, this turns out to be a quadratic equation. This turns out to be a 5th degree equation, which is way beyond, even college algebra students don't face this until about right now in the semester. We're just now getting into things like this in college algebra. So, see what I'm saying? We can't do this. So that limits what you'll see in terms of radical equations to what I just showed you today. That's pretty much it. Okay? So there's a homework assignment on our schedule. I'll just put it on the board for that section. Can I check this real quick? Just want to make sure I can do the right thing. Page 570. '21 through 21 through 41. Page 3 or 570. 21 through 31 odd. That's good enough for what we're doing. All right, so how is this so far? I mean, other than me tripping over my own wires and stuff, are y'all, is this okay?
I like this more than the previous
Okay.
times. Sure.
Oh, this, okay, y'all got it? Yeah, I mean, this is where I'd rather be, is in front of the board, in front of the students. This is where I'd rather be. But, you know, I'm just trying to keep up with everything and the way things are going these days in technology and, you know, trying to get everything out there for my students, you know. Sometimes it doesn't work.
In this method, I've noticed.
Well, I have to, I think, right?
Yeah,
I can't just hide behind my computer over there.
It's not just some virtual overload. Passing down information.
Watch the screen and listen to me. All right, well, we're going to do our survey in a little while, but I still want to start covering, since we weren't here on Monday, right? I gave you that day off because I accidentally gave you that day off on the calendar. Yeah, anyone who missed Monday, you didn't miss anything. So let's see. We are going to actually start what we were supposed to do. Where is it? Let's see. We're going to start 10-1. Okay, so everything's going to be pushed. On the calendar, everything's pushed up now one day. So 10-1, though, a lot of you have seen. It's complex numbers. So let's begin. 10.1, complex numbers. I find it very challenging to teach complex numbers because I have a very, very deep passion for complex numbers. So it's hard for me to just not go off topic and just go run away with this idea in my classes. So just be prepared. I'm probably going to go off on a tangent here, and that's just the way it always is with complex numbers, all right? But we'll start with this simple definition. All right, for a long time, the question was, did that make up, like, when I say the question, like human beings, right, at some point ask this question, does this make sense to say the square root of -1? So the problem with it is if you compare it to something like square root of 4, we know the answer that's 2, because when you square 2, you get 4, right? But it would be impossible for us to find a number that when I square it, I get back a negative number. We've talked about this before, haven't we? Because no matter what number I ever choose, that number times itself has to be positive, doesn't it? Yes? That number. Like even if you try to say this is -1, it can't be. Because what's -1 times -1? 1. It's +1, and that's not -1. So you can't say it's -1. And of course it's not +1, because +1 times +1 is also +1. So for the longest time, this was just kind of, well, doesn't make sense, doesn't happen, can't happen, who cares, right? And then some mathematicians came along and started to mess with it some more, and they said, yes, we are going to just call this I. Whatever it is, we're going to call it I. And the I stood for the imaginary unit. So the I here comes from I in the word imaginary. And so there was a big group of mathematicians and scientists who were like, those guys over there that are messing with this imaginary, like, these guys are crazy, okay? Because it is. It's like your imaginary friend, right? The one that sits on your shoulder and tells you everything you need to do, right? Everyone has an imaginary friend. Come on. Everyone has an imaginary friend? I'm the only one who has an imaginary friend? See, it's absurd to talk about imaginary friends, right? I mean, it's absurd to talk about imaginary numbers, and that's the way it was looked at for a long time. And then later on, it was proven that the imaginary numbers exist and that they are as valuable as the numbers 1, 2, 3, 4, the numbers that you deal with all the time, all right? But it's beyond the scope of this class to see that happen. Like, it's way past this. Even in college algebra, we just mess with them a little bit. So we have this imaginary number, right? This I now represents for us in this class, I is always going to be the square root of -1. Anytime we see square root of -1, it's I, okay? So how can we use this to solve problems like this? Square root of -4. Well, we use the property that we had before, that you can always split up 4 into 2 numbers being multiplied, right? So how about making it 4 times the square root of -1? Isn't that right? Right? What I'm doing is I'm splitting 4 up into 2 numbers and being multiplied. 4 times -1 gives me -4. So I'm pulling the root apart into 2 pieces.
Couldn't you just put it in the same bracket? For I?
Well, what's the square root of 4 though?
2.
2. So this would actually be 2 times, now what's square root of -1 for us? I. 2I. That's it. That's the answer. I'm asking you to swallow a pill today, and the pill is basically that you are going to accept that the square root of -1 is I. You're just going to accept that.
So 2 times I. That's it.
That's it. The square root of -4 is 2I. But I is no longer a letter like an alpha, I mean, it's a letter, but in mathematics, I doesn't represent anything except I is the square root of -1. That's accepted. Have y'all ever seen the number pi before? Y'all heard pi before? Pi is a number, isn't it? They always tell you. It's like approximately 3.14. Approximately. That's what squiggly equals means. It's approximately 3.14. So pi is a number, but pi is a letter. It's a Greek letter, right? So anytime in math that we take a number and represent it with a letter, that means it's an important number. So pi is one example of an important number. Has anyone ever seen this number before? E? Have y'all ever heard of E before?
Isn't that?
Has anyone ever heard of a natural log? Maybe not. Okay. E and natural log are like opposites of each other. So E is also a number. It's 2.718, approximately 2.718. So that's another number that's so important we give it a letter. Here's another number that's so important we give it a letter. The square root of -1 is the number that you get when you try and take square root of -1, and it is now represented with I. Okay. Let's try something. I mean, all you're going to have to do is be able to basically go from here to here. There's not a whole lot more for us. So this section is not going to be too much of a stretch, but we can run into things like this that require a little more work. Now, before we said there's no real answer, right? We'd say for this, no real answer. Why? That's right, because you got an even power on a negative number inside. We said we couldn't do it before, but now we can. So I'm going to split it up first, and you'll always do this. Split it into 2 square roots. One of them will have your negative in it. The other one won't. We already know the square root of -1 is going to turn into what? I. Okay? Over there, though, what do you have to do with 80? Break it up. So we used to break up 80 like this. 80, then we would do what? Try and come up with a number that goes into 80, but that's a perfect square.
4 times 20.
4 times 20. Is that the biggest perfect square we can get in there? Isn't 24 times 5? Right? So isn't there another 4 in here somewhere that I can put together with this 4 and get a 16? But 16 and something gives you 80. What is it? 16 and 5. So either 4 and 20 or 16 and 5 would work. I'm going to go with 16 and 5 because it's the biggest square root I can, or the biggest perfect square I could possibly get into 80. So now we get our square root 16, square root 5, square root -1. Square root of 16 is what? 4. Square root of 5, I don't know. And the square root of -1 is I. Now, that's correct, but here's the way we'll write this. We'll put everything out in front of the square root of 5. And you always put the letter I behind the number. So it'll be 4I root 5.
So
That make sense?
Okay, so that letter I always goes in front of that 4 outside that.
Well, it'll always go in front of the square root. If there's a root in there, put it in front. But if there's a number, put it behind the number. Just like we'd write like 3x. You never put x in front of 3.
Right, okay. So is the I never going inside of the square root?
The I will never be in the root. No, not in here. All right? Pretty straightforward, right?
So,
no.
is there going to be homework on this 2.1?
Yes, I'll give you some stuff to
Oh,
do.
so you're going to use some examples?
Yes.
Like figures and things?
Yeah, we will. We're going to do more. I'm not done yet. We still got a little more to talk about. And then I'm going to give you that survey and the final homework assignment. Here's what I would like for you to see, though. I need you to see some properties of the I. Okay, there's some stuff with this I that's kind of interesting. We said just now I is equal to the square root of -1, right? That's what we said? Okay. So what then would be I squared?
Square root -1 plus square root -1.
Now this is where things get a little bit weird, okay? You have to, what did we say? We said the square root of -1 is something, right? It's something that when you square it, you get what? When I say the square root of 4 equals 2, I'm saying that when I square this, I get what? 4. So when I square 2, I should get the 4. So if I'm saying the square root of -1 is I, then when I square I should get what? -1. Agreed? I is the number that when you square it, you get a -1. That's the fundamental property of I. It's the only number that when you square it, you get -1. Okay? Everyone's kind of got that dull look.
Is it -1 times -1 positive 1?
But I'm not saying that. I'm saying I,
Squared.
when I square I, not with -1. When I square I get -1. There's no number in the real numbers that can do that, right? The real numbers, all the numbers you've known your whole life, none of those numbers can you ever square it and get a negative number. But if you bring into the mix the imaginary numbers, then you can. what about if I cube I? What would I get? Tell me if you believe this. Do you believe that I cubed is the same as I squared times I?
I would think so.
Right? That's like x squared times x is x cubed. Right? So I squared times I should be I cubed. But what did we just say I squared was? -1. And what is this? What is I? I just square root -1. So I'm just going to leave it as I. -I. Right? I cubed is I squared times I. I squared is -1. -1 times I is just -I. What's I to the 4th power? Well, isn't that I squared times I squared? Isn't that -1 times -1? And what's -1 times -1? Positive 1. So here's what I'm going to do. I'm going to go back up here. I is this, right? By definition, that's why I defined it right at the beginning of the section. So I is basically I, okay? I is I. When I square I, what do I get? When I square it, what do I get? -1. When I cube it, what do I get? -I. And when I raise it to the 4th power, what do I get? 1, right? You with me? Now, right here, I'm going to write I to the 5th power. Isn't I to the 5th I to the 4th times I? Isn't it? Still agree or not? Okay. What's I to the 4th?
1.
1. What's 1 times I? Just I. What? I'm going to stop eventually. Hold on. I to the 6th. Isn't I to the 6th I to the 5th times I?
So you didn't stop there?
Oh, hold on. What's I to the 5th? It's I, isn't it? And then isn't I times I squared? And what was I squared? -1. Something is happening here. Do y'all see the pattern or not? What's happening? Isn't it starting to cycle and do the same exact thing? Look, I by itself is I, right? So I to the 1st power is I. I to the 2nd power is -1. I to the 3rd power is -I. I to the 4th power is 1. I to the 5th power is I again. So now I'm here. I to the 6th, -1. I to the 7th should be -I. I to the 8th should be 1. I to the 9th should be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So what's happening here is you're getting this cycling happening. We had the same exact pattern on the number -1. -1 to the 1st power is -1. What's -1 squared? What's -1 times -1? 1. What's -1 cubed? -1. And then -1 to the 4th? 1. Right? With the good old-fashioned -1, when you raise it to an odd power, you got -1. When you raise it to an even, it got 1. So it kept on cycling back and forth, right? With I, you get that same cycling, except that it cycles through 4 things, and then starts cycling again, and cycling again. Y'all see that? The most important one for you to know here is this one. I squared is -1. And let me show you why it is that that one's important.
Here's one on the imagination.
Find what this is. What's -10I times 3I? Okay, so you're going to do all multiplication here, right? There's no addition signs anywhere. So do your negative 10 times 3, and that would be negative 30. And what would I times I be? I squared. Well, what did we just say I squared was? Negative 1, right? So yeah, so it's multiplication there. So this is going to be negative 30 times I squared is negative 1. Multiply negative times negative is positive. Your answer is 30. So negative 10I times 3I is 30.
That's why it's important to know that I squared is negative 1.
That's right.
That's how you do it.
That's how I got this, right there. And that's what you're going to have to be able to do also. Here's another example. Find what this is. What is negative 2I times 7 minus 3I?
We're defining it in the parentheses first.
Well, can we put these two together?
No.
This is like a 7 minus 3x. You can't combine these because they're not like terms. So the only thing you can do is distribute this multiplication through. So what would you get here? Negative 2I times 7.
14.
Negative 14I?
Yes.
All right. And now, how about the second multiplication? What's negative 2 times negative 3? Positive 6, but then
Squared.
I squared. Because I times I. And I squared is negative 1. So this is negative 14I plus 6 times negative 1. 6 times negative 1 is negative 6. Negative 14I minus 6. That's it. See how that worked? Okay, one more. What about if I ask you to find 2 minus 3I squared? So by squaring it means it times itself, right? It does not mean you square each one, right? You don't just square each one, you have to do the FOIL, don't you? So 2 times 2 first gives me 4. 2 times negative 3I gives me negative 6I, right? Because all you're doing is a 2 times negative 3. The I just comes along. What's the middle multiplication give you? Negative 6I again. And then what about the outer last, or I should say last ones? Positive 9, I squared. However, I squared is negative 1. Also, what about these two?
Cancel.
Not quite. If they were opposite sign, they would. They combine to give you how many? Negative 12I. Good. So we have 4 in the beginning here, 4. We have minus 12I. And then we have plus 9 times negative 1. And the 9 times negative 1 is really going to be a negative 9, isn't it?
What did you just say?
This 9 times negative 1 is going to be a minus 9.
Right.
Okay.
So
So
that we're not, is that it?
no, we're going to put it together with that 4 up in the front. See, because we have a 4 up here and then a minus 9. We can't do anything with the negative 12I.
So it just means negative 5.
Negative 5 minus 12I. That's it. So negative, 2 minus 3I squared gives us this. Okay?
For now, are you gonna have the eye?
Squared, yes. Pretty much, well, I need to double check the homework. You might have one of the other ones in there, I cubed, I to the fourth. Just go back to that what I put up here and just, if it's I to the fourth, it turns into a 1. If it's I cubed, it's negative I. So I want to end with this because I did a pretty good job of staying on track here and not going too crazy. But I'm going to go ahead and I want to show you something. Okay, there's this kind of philosophical idea. I like to call it the fishbowl idea. This is a fishbowl. Pretty good fishbowl, and that's an even better fish, right? That's my fish, right? And I'll put a couple other fish in here with them.
So you're writing this down?
You don't have to. Okay, there's all my fish, right? In their fishbowl. Now we know that fish don't think like we think, right? But I think you can follow what I'm saying here. To the fish, their universe is that bowl, right? And that's their universe. Their existence is inside the bowl. The fish in a bowl would not realize that you get up and you get into a car and go to work, and they just have no concept of anything outside that bowl, right? Would you agree?
Yes.
Okay. You could think of the same thing of animals that live in the ocean, right? The sharks and the whales don't really have the idea of the mountain goat, right? It's just not even in their thinking, right? The shark doesn't swim around and think about, I wonder what the camel's doing in the desert today. They just can't, they don't fathom that because it's not in their world. Their world is the border of the bowl. Okay, the way that you've been raised, which is just fine because it's the way we have to raise everyone, okay, is to believe that all numbers that exist are the numbers on the number line. And that's your fishbowl. That's your fishbowl, right? And today I'm introducing this new number I. And we call it imaginary. It got a bad rap in the very beginning. It was given imaginary. Everyone thinks it's just silly. But I'm here to tell you that just like the fish was sitting here saying, hey, yeah, there's this mountain goat. And the other fish are like, all right, whatever you're doing, go ahead and keep doing it, all right? Okay? There's actually there is a mountain goat, okay? Right? And over here, the I is very real also. So in the fishbowl that you live in, you think these are the only numbers possible, but the imaginary numbers live out here in a bigger universe of numbers that we call the complex numbers. The ones in here are called real. And that's why I've said before the real solution, there's no real solution. That's because there is not a solution if you live in the bowl. If you live outside the bowl into the complex numbers, then there are solutions to a lot of things you can't do here. Okay? I'm just trying to get you to see that in a lot of things in the real world, as you learn more and as you progress, you realize that a lot of times you're in fish bowls, right? That's just the way it is. I'll give you another example of the fishbowl idea. How many of you are familiar with parallel lines? Parallel lines, right? Okay, so if you were trying to explain to me or someone else what parallel lines were, what would you say? Like if I draw that, what would a parallel line have to look like? Next to it? They don't ever touch, right? Parallel lines shouldn't intersect each other, right? Would you all agree with that?
Yes.
So if you were on like Who Wants to Be a Millionaire and that was the question, parallel lines don't ever intersect, true or false, you would say true, right? They don't ever intersect. Well, again, that's in your fishbowl. In the fishbowl of life, most people think that parallel lines don't intersect. But how many of you are artsy people? Or you've taken art class or you enjoy art? Nobody? Nobody likes art at all? No? Okay, then I'll phrase it this way. How many of you ever looked at like a kindergartner's art or like caveman drawings versus like art that's out there more modern, right? They kind of sucked at drawing back then, didn't they? And even little kids, they kind of suck at drawing too. You know what I'm saying? Everything's stickman, flat. It's just terrible, isn't it? So how is it that people get good at art? Well, one of the major breakthroughs was to step away from this sort of idea and this sort of geometry, step outside of this fishbowl, and to realize that if you're going to try and trick the human eye into seeing something on a flat piece of paper, parallel lines can't follow that rule. So I'm going to take, this is one of my classic things I do. This is a road looking from the top, right? And this is, let's say, a couple of buildings sitting on the side. These two lines on the road are parallel, so they don't hit, right? These buildings' walls are parallel, they don't hit. They don't hit. Everything's drawn perfect, but that's a crappy picture of a road and buildings, isn't it? Not very advanced. Agree? Okay, so step outside of the fishbowl now and watch this. I'm going to create a point, which art people call the vanishing point. And the rule now is not this. The rule now is that all parallel lines all go to a single point. And it goes to this point. So here's my road. The right side of my road must go there. The left side of my road must go there. The center of the road must also go there. Right? Then you have the buildings on the side. All those lines have to go there. Now I'm going to go fast because we're running out of time. Right? All my parallel lines are going to go towards the vanishing point. Right? So now I'm starting to create depth. And I'm starting to get a much better picture than this, right? Here I was fixed in the bowl. Parallel lines can't meet, can't hit, right? That's the rule, that's the rule. Step out of the bowl, you can make other things happen, okay? I want you to value the eye and not just think of it as the imaginary friend in the room. It is as valuable in mathematics as it is this idea. Get it? All right, we're going to do our survey. Let me turn off my, wonder how this is going to come out.